Okay, so next we have Amandine, she has a long title for us, Feedback from Active Galactic Nuclei in Galaxy Groups and Simulating Groups and the Intragroup Medium, the surprisingly complex and rich middle ground between clusters and galaxies. So please, Amandine, I'll give you a 3-minute warning.
Thanks a lot, Adrianne. So I'm really glad to be back among you. Some people might not even remember how I look like. Sorry, I cannot put my camera on today. The reason why you haven't seen me since 2017 is I had to take a really long career break for health reasons. And I'm back since January 2020 as a PSL fellow at the Paris Observatory, but still working part-time for the same reason. So you will have to bear with me because I'm still tiny bit out of practice. And today is not a good day to show my face. Hopefully tomorrow when I'm sharing, you can see my face. So sorry about that. And I've been given the difficult task to summarize 250 pages review out of a 250 pages special issue on groups in less than 15 minutes. So we better get started. Oops, now it's changing. So it's part of this special issues entitled The Physical Properties of the Groups of Galaxies. It's from the journal Universe. All the links in these talks are clickable. Basically, all the references are clickable links, which will take you straight to the paper in question. It's made, the editors were Lorenzo Lovisari and Stefano Ettore, and it's made of 5 reviews, as I said, with a small foreword, talking about, a short note before I get started. In most cases, all authors contributed equally to the reviews they were involved in, and it's indicated in the authors list of each review by a small dagger. So basically, it's a first author paper. It's so much work, a 50-page review, even if you're 5 authors. So the small forward is why groups, why now, basically. And it has basically, because they made up most of the matter of in the universe, they are the best place for testing structure formation and on the non-gravitational processes. Therefore, they're also the main source of systematic for cosmology, and there will be an onslaught of data on groups in the next few years. So it's really timely to review our current knowledge, and it's never been done. Piles of reviews about clusters. There is not a single review about all the aspects of groups. There's a single attempt, and it's just an X-ray observation. It was back in 2012 by Mingson. In that forward, you can find a 5-line summary of each of the review, if that's all you read. And I've highlighted for you the abstract of each review. So you have the first one is about scaling properties. The second one is on their metal contents, because with the upcoming X-ray missions, we'll know even more than we do now. And they are a main source of systematic for things like mass measurements. Groups are, there's a special category of groups, which it's called fossil groups. It's basically an intermediate between groups and big ellipticals. It's basically the central group galaxy that has swallowed all its neighbors, and it's just become a big elliptical who no longer does anything. And here are the 2 reviews I'm going to try to talk about in less than 10 minutes. So the simulation one and the AGN feedback in groups, which are basically 2 sides of a coin. One is So this one I was part of is both simulation and observation, and the other one is only focused on simulations. So what we try to do is also to try to make it useful for the community, and we restarted for why is a case for why we think AGN feedback is important in galaxy formation, and especially why groups are so important for constraining it. And we went back to the beginning, and AGN feedback, the idea is nearly as old as structure formation itself. It's from the late 70s, but it took 30 years for people to realize it was a solution to a lot of problems. And this particular plot, which is the one that shows you that if you only if you scale down, that galaxy formation is basically inefficient at both ends, which is where the idea of feedback was first introduced back in the 70s. If you take the Tinker mass function, you scale it by the halo universal invariant function, you obtain the dashed line. And if you compare it to the Cosmos data, this double Chester fit, which is the blue dashed line, you see that you have a problem both at the low mass n, which we know now to be solved by supernova feedback, and either high stellar mass n. And we know now that for that you need AGN feedback. And that plot, I couldn't, the youngest version I couldn't find was Benson 2001. So we updated it with new simulations and new data. So feel free to use it. The other realization that was made during that whole process of thinking about this problem on the galaxy stellar mass function, it was that AGN feedback was basically a solution to a lot of issues, which turned out to be all different facets of the same problem, basically cosmic dosinding, the shape of the galaxy stellar mass function, as I highlighted, the gas content of massive galaxy groups of cluster, absence of a cooling flow, which was realized in the late 90s with the advent of XMM and Chandra. We didn't see the cooling flows we were expecting. The deviation was of some self-similarity of gas scaling relation and the entropy floor. So we show example of all that. And besides, we had huge, as from the late 90s, from XML and Chandra, we had huge observational evidence from shock cavities, bubbles, and so on and so forth. So here you have a Chandra image and temperature map of a huge elliptical. It's the deepest observation that we have in X-ray from a single huge elliptical. It's 650 kiloseconds. And you see a lot of feedback-induced features, so that shock, cavities, both in the image and in the temperature map. So you have the theoretical perspective that's saying that you need something, you see something on the other side, maybe both are connected in some way. And the other thing that we had is that we realized that the power in the cavity was in a scaling with the cooling. So maybe it's because one offsets the other and they are in a self-regulating loop. Other bizarre things is deviations from self-similarity. For that, I point you to the full review on scaling relations. But what you can see here briefly is the entropy, which is basically the temperature of the density to the 2/3 as a function of temperature. And if it was subcellular, it should be a straight line. And you clearly see that at low temperature, meaning low masses, it starts to deviate. So there are too high entropies in the groups. And it's valid at all radii. So something is going on that's heating up the gas and changing and creating this entropy floor, basically. And also, groups are super. So the thing we did, we compiled all the existing observations of groups for some scaling relation, like the gas fraction as a function of mass, as well as one for clusters. And this gray shaded region that you can see on this plot is what encompasses 90% of the data, and it's made freely available as a fit that you can do on any of your plots in the paper. And you see that they are devoid of gas, so compared to the stellar fractions, even though they are higher than in clusters, don't make up for the difference. So all that points to the fact that AGN feedback is probably something we need to think about. Here is the same thing but seen in the radio, because sometimes X-rays, it's a bit hard to see the AGN feedback in X-ray in some condition, and radio is a really highly complementary way of seeing things, and you can learn a lot about the things about AGNs in that way.
Three minutes, Amandine.
Yes. I will really speed up. There is a huge section about all the theory that linking all the scales and how we think it works. And so I'm only going to show this summary plots. And we computed what we think should be the energy that should be coming from the black holes in order to reconcile what we see and what it should be in terms of binding energy. And here is where I came in, as well as doing the history of AGN feedback and structure formation, is compiling all the results from simulation. We sorted them into 3 categories. High resolution simulations, we can learn a lot with them, but not good for having samples and doing cosmology. Moderate resolutions, which are not, which I will, low resolution in big boxes, and that are quite often now calibrated. I will split the simulation in between two further categories, which is the modern, which is the one that have been run after 2014, which are often calibrated on the galaxy stellar mass function, and the one that came before. And the funny thing, even though that idea was 50 years old, it's only in 2008 that we had the first simulation with AGN feedback for groups, the simulation from Pudgebank. So here's the F-gas versus mass plot for this historical simulation. They come in different flavors, and you have the gray shaded region of the observation beneath. Sorry, I won't have time. Same thing for the modern ones. And what you can see is, even though most of the simulation have been calibrated on the galaxy stellar mass function, that doesn't guarantee you get the gas content right. And so one of the things that's going to be the hardest for the simulations now is to get both right. And I will unfortunately have to skip all that, so I'm skipping the, and here are the messages I would like to take home. As I said, all references are clickable. Groups are way more important than just the intermediate scale between clusters and individual galaxies. The ideal targets for constraining feedback mechanism, key to our understanding of structure formation. The influence of those potentially complex and difficult to model and reproduce in simulation, despite the fact that in recent years we've learned a lot of things, and we're getting closer to understanding. And now the challenge is to have both realistic galaxy population, which we are getting close to, while also reproducing the gas properties. And I will leave you with that.
Thank you. Thank you, Amandine. Do we have any questions for Amandine? So quick question.
Sure.
It's a very general question. So can you summarize, you were trying to convince us that we should look at galaxy groups. Can you summarize, are there any major ways that they differ from the clusters in all these scaling relations and other things that you looked at, other properties?
For instance, apart from this, the entropy profiles, basically everything is different in groups. You have the central galaxy is way more dominant, so you have much less satellites. The slope of most of the scaling relation is not the same as the one you have in clusters, which is much closer to the self-similar expectation. So that's how people realize that something must be going on, because they saw that that the scaling relations were broken. You had one regime for the groups and one regime for the clusters. So it must be something that's creating a particular scale in the middle.
Okay.
And it's basically where supernova feedback becomes completely inefficient. And
Thank you. Wonky has a question.
Yes, thank you for your great presentation. I have a naive question, maybe I missed, but can you comment on how observation can measure the gas fraction, as we are going to see a colder gas than clusters, and X-ray observation will have like more challenge to measure those masses. So,
yeah, that's a tricky one. Yeah, you're right. I unfortunately didn't have time to go into the details, but there is a lot of systematics in there, and it's even worse for estimating the total masses in the mass of gas, because you have to do a lot of assumptions. And the cold gas, we haven't seen much, so it's a minority correction compared to what is shining in X-rays, at least in the central regions. We now have cold gas observation coming from ACA, ALMA, and a lot of radio observations. And apart from the region where you have star formation, you don't have cold gas, and of course along filaments.
Okay, thank you very much, Amandine. And so let's move on now. Let's invite Marta to upload her slides.
Okay, I think that you should be able to see them. Good.
Perfect. So next we have Marta Volonteri telling us about the dynamics of massive black holes in cosmological simulations.
Thank you, Adrianne. Thank you to all the organizers. And let me start by saying that I'm only the designated presenter, but really the work here has been done by this group of people. Ricardo, Johan, Sandrine, and Ugo have worked with Ramses, and Michael Tremmel, we have worked with Changa. So let me first introduce the problem, which actually was already touched upon by the question that Christophe asked to Hugo, which has to deal with the scales of massive black holes in galaxies. So when we talk about massive black holes, we talk about these black holes that sit in galaxy centers, Sagittarius A star, for instance, in the Milky Way, and M87, with the famous picture like the donut that we have probably all seen. But if you think of these objects, again, the EHT and gravity, these instruments have to really zoom in the center because black holes are tiny. So if you think of a galaxy like the Milky Way, the size of the dark matter halo would be something like 100 kiloparsecs for a mass of about 10 to the 12 solar masses. The luminous part of the galaxy is about 10 times smaller, both in physical scale and in mass. But then when we look at black holes in there, then they're really tiny. Now, the mass of black holes typically is about a factor of 1,000, 10 to the 4, smaller than the stellar mass. Just to give you an idea, so for instance, the black hole in the Milky Way has a mass of 4 million solar masses. I mean, it's a bit under massive, but it's okay. But then the physical scales that are reported here, there are three main scales: the Bondi radius and the radius of influence determine the radius within which gas and star, respectively, follow the potential determined by the black hole. And then we have the Schwarzschild radius, which is the event horizon. And you see that these scales are all very small, from parsec to microparsec. I mean, the reason, especially for the Schwarzschild radius, is it scales with the speed of light, which is a much larger number than the sound speed of the velocity dispersion that we have in the other two equations. So it's something. So if we wanted really to understand the dynamics of black holes in galaxies and even more in the cosmological context, we would have to resolve down to microparsec scales, which is bit difficult if we want to resolve the whole galaxy, or even more, a few megaparsecs of the universe. Now, why should we care about this? And I usually think of this. There are people that struggle, but most people are either galaxy people or black hole people. So if you're a galaxy person, you may have a galactic center attitude. So you really want, as Amandine just said, black holes emit energy. So with agent feedback, they shape the star formation rate of their galaxies. And so you need the correct agent feedback to have the correct properties of galaxies. And if you're like me, you're a black hole person. And so you really want to have the correct properties of black holes and of their mergers. And their mergers in particular is important in the current era, where we're moving towards low frequency detections of gravitational waves from merging massive black holes. Now, an important point that I want to make here is that very often you can have the right amount of agent feedback to make galaxies look good, but have the wrong AGN black hole population. And this is the case of TNG. So it's not a one-to-one connection, but ideally, if you like galaxies and black holes, you want both to be correct, or at least to be realistic. And so this is the goal that we have. And I just want to note here, there's this paper that came out just a week ago analyzing this, and before Johan and Booth and Shea have worked on this. When regarding the black hole properties, this is mostly done in our group. Okay, so let me give you some examples. Black hole dynamics and agent feedback. The reason why dynamics, so the way black holes move, is so important for agent feedback can be related to the way in most simulations, and I think in pretty much all cosmological simulations using Ramses, the accretion on black holes is modeled. Usually we use a modified Bondi-Hall-Littleton formalism, well, modified just because it's numerical and it's not analytical, and you're not in the correct analytical setup. But you see here it scales with the black hole mass, the gas density, the sound speed, and the relative velocity between the black hole and the gas that is moving. And then the feedback luminosity is proportional to this accretion rate. And so in this figure taken by a paper by Johan et al. In 2012, I think Adrianne was in it as well, you can see how limiting this relative velocity, I think that this was really a seminal paper because at the time I was stunted by this problem. And here they show how limiting this relative velocity really changes the star formation rate and really changes the way the black holes grow. So if you allow for a high relative velocity between black hole and the medium, the accretion rate drops. And so the black holes don't grow, don't emit feedback, and so your star formation rate changes dramatically. On the side of black holes, we have even worse problems in some sense, because really this is the heart of the matter. I mean, from the physical point of view, you know, when we think of merging black holes after galaxy mergers, this is really a very rich physics, which is why I like it so much. And here I just highlight, you know, here you have a galaxy merger, and then you want two black holes eventually to merge. There are different physical properties that happen, physical processes that make this happen on different scales from kiloparsec to milliparsec. And here I just highlighted with these sketches how uncertain all these physical processes on all these scales are. I mean, it's not that the physics is uncertain, but how the physics couples with the environment where the black holes live. Most of the analytical formulas was derived for a homogeneous infinite medium, which is not what a normal galaxy is, especially it is during a merger. And so this is the challenge that we have. And you see here again, it's a significant problems of scales. We start from large scales, the merger of the galaxies. So here you need a cosmological simulation, and you need a statistical sample, so you will need a large volume, and so this limits your resolution. So in this case, the only thing that you can follow is really the merger of the two galaxies. If you want to follow the mergers of black holes, it happens on milliparsec scales. You need to use different techniques. So for instance, you know, moving to the other extreme, we have simulations in numerical relativity of the merger of few black holes, the emission of gravitational waves. I mean, they are beautiful, but they have a size of a few Schwarzschild radii, and they cover this for a few orbits. So a few days in, you know, and we think the universe is 13 billion years. So that's why we need also intermediate scales, so different types of simulations that really cover these scales. And the main problem nowadays is that we don't and probably cannot have a single simulation covering from the numerical relativity all the way to the cosmological scales. So this is why this has been a huge problem, a huge headache. And let me focus today on this particular intermediate scale. Well, mostly because this is the one that we as a community have been able to tackle recently. Now, the forces, the main force that we think black holes experience, or any heavy object really, when moving in a galaxy is called dynamical friction. It's highlighted here. If you have an object moving in this direction in a homogeneous distribution, homogeneous and infinite distribution of stars or gas, but this is easier for stars. The imbalance of the force in the tangential direction create a force directed in the opposite direction compared to the velocity of the black hole or the perturber. So it's a friction, it slows it down. Now, an intuitive way of understanding this is that the particles, so the stars in this case, accumulate behind the moving object, creating a wake that drags it. So you have an overdensity, an extra inertia behind the object. But the region where this overdensity occurs is very tiny. For a massive black hole like in the Milky Way, it's about 1 parsec. So clearly, you know, if you don't resolve 1 parsec, you don't capture completely this force. And so your dynamics of the black holes, your force will be underestimated. Now, I just showed you that the spatial resolution needed for just intermediate scale, let me remind you that this is the intermediate scale, it's not the scale where black holes merge, is a fraction of a parsec to a parsec. But most simulations, even high resolution cosmological simulations have resolutions of tenths of parsecs to kiloparsecs. I mean, something like New Horizon is an exception, it's very high resolution. Besides spatial resolution, also mass resolution is important. You have to avoid spurious scattering, shot noise. So the mass of the perturber, the black hole, must be at about 10 times larger than the mass of the other particles, unless you smooth their potential. And again, if black holes at birth, we believe that the black holes at birth are a mass of about 1,000 to 10 to the 4 solar masses. So you clearly see this puts a very strong constraint on the mass resolution of your simulation. So this all boils down to being a headache, as I said. And so historically, there have been two main approaches. One is to artificially move black holes to the minimum of the potential well. This is done in many of the large simulations, such as Illustris, Illustris 10G, Eagle, Massive Black, or Blue Tides. Or account for the missing force. So include this dynamical friction subgrid. And this was done in Horizon Again, Horizon, and Romulus. So this is just an example of an advection case. This is a movie of Michael Tremble. Here, if you have advection, poof, as you see, black holes are moved, poof, at very high velocity the moment they get close to another black hole. And so, although this fixes the problem of understanding where black holes go, it has the problem that black holes are, as Michael would say, teleported at speeds sometimes larger than the speed of light. So for instance, you see in this plot, which is not exactly from the movie that I showed you before, but it's similar. It's the distance from black holes, a function of time, again, a cosmological simulation of a dwarfish galaxy, highlighting the times when black holes merge. Now, my favorite black hole is the green one. You see here, this black hole is at some point at about a few kiloparsecs, poof, it's teleported within one time step at the center of the newly formed galaxy and merges with the other black hole in something that is perhaps not super realistic based on what we know about the speed of light. So there is a second option to treat dynamics of black holes. I said to add subgrid the force that is missing. This was done by Michael Tremble and for Changa, by Yuan even earlier in 2012 for gas, and by Ugo for stars and dark matter in Ramses. So basically, you calculated the force that you should feel because of the distribution of stars and dark matter and gas, although I will touch on gas if I have time in a minute. And you simply add it to the black hole so that it can move more naturally. So this is the same movie from Michael earlier, but now we don't have advection, but dynamical friction. And you see that the black holes, perfect, yeah. You see that the black holes, instead of merging with each other, being teleported at rapid velocity, they just move around. So this has the consequence, of course, of black holes not merging so quickly. And so sometimes you have what we call wandering black holes. So going back to the same simulation that I showed you earlier, but with dynamical friction, the green black hole that here was teleported to the center and merged now does not merge with the other black hole at all. It just on a very wide circular orbit, and so nothing happens to it. I mean, it's sad the black holes don't merge, but this is actually what we expect from their orbital evolution. A corollary of this is that, usually when we think of dynamics in galaxies, we imagine these nice, smooth, ellipticals or spirals with beautiful potentials that you can integrate analytically and obtain a time scales for the orbit of black holes to reach the center from a large scale. But when instead you calculate the force directly in the simulation, you face that hierarchical galaxies are all but something like this. They look like messy little things without a galactic center. And so also the orbits of black holes become something that we call erratic. And so this is all, something that we are learning about. Something that I don't think I have time to touch on is dynamical friction from gas. Ricarda has worked on this. She's done beautiful work trying to understand what we need to resolve dynamical friction from gas. And more recently, we have been looking at the evolution of turbulent medium. which is what we expect in a galaxy rather than a homogeneous infinite medium. One last point, I will just mention it very quickly, that feedback from the black hole is also affecting its own dynamics. It disrupts these wakes, this dynamical friction. And so this is something that is important and it's been started being studied in the last few years. So, I will just leave here my summary. I mean, it's a difficult problem. We haven't got to the end of this, but at least we have highlighted some of the problems and some possible solutions. I think that with stellar dynamical friction, we kind of have a hang of it, but dynamical friction from gas, especially under the effect of feedback, is still something that we have to understand. And really, I think that for this, we will always need high resolution simulations, and I will stop here.
Thank you very much for a very interesting talk. Are there any questions for Marta? Please raise your hand. Suk-Young.
Yes. Marta, thank you very much for the talk. And you mentioned that a very clumpy structure of galaxies at high redshift. In such turbulent galaxies, black holes will have difficulty settling down at the center. I agree with you. In addition to that, even if the galaxy appears to be smooth and nice and well balanced, symmetric, if you look at the gas motion and gas distribution at the very center of the galaxy near the black hole, and the motion of gas and the distribution is very lumpy, and so relative speed between black hole and gas could be very high, right? Yeah. So in a apparently a smooth galaxy, black holes might have difficulty settling down at the center. Would you agree?
Yes, absolutely. Again, this is a stellar distribution, but if I showed you this, the gas distribution of the star would be even worse. And as you said, in some cases, the galaxy looks relaxed from the stellar structure, but it's not from the gas structure. So this is a serious problem. Now, something that we haven't tried is to use something that is not Bondi-Hoyle-Littleton motivated in terms of accretion. If the relative velocity doesn't enter in your accretion rate, perhaps, Daniel Anglès-Alcazar has done something in the fire simulations. But, from the physical point of view, I think that this remains a problem. And as Hugo said, perhaps accretion of stars can help a little bit. There is also some work that Pavel Bernatschke has done with Romain Tessier, showing that if you have a stellar cluster around the black hole, that can also help settling in. But I think it's I don't have an answer. I don't even know how to ask the question, really.
Thank you. A quick question, last question from Amandine, please.
Yes, Marta, thanks very much for the really nice talk. A bit more of a philosophical question. Do you think we'll one day manage to reconcile those two sides of those 2 points of view of about black holes?
I've been trying for years. So
I know.
If there are more people who are, willing to put black holes in their galaxies and galaxies around their black holes, I think that would be great.
Because on top of having, as I shown, having the galaxies right doesn't mean you have the gas content right. Now we also have the black holes that are not right unless we tune them to be right. So I don't know. It's starting to be a bit too many problems.
But it's a multi-scale, multi-variable problem. I mean,
I know, but it was bound to happen in a way, I guess. But
either we give up on galaxy evolution or we try.
Yeah, I don't think we should.
Thank you.
At least not yet. So it was more a philosophical debate than a question. Thanks a lot.
So let's now invite Taysun. Excellent, he's good to go. So Taysun is going to talk to us about Lyman continuum and Lyman alpha escape from giant molecular clouds.
Okay, can you hear me? Yep. First of all, thanks for organizing this workshop. I guess many people wanted to have this because this is probably was the friendly environment where we can share ideas about numerical simulations. And today, in about 50 minutes or so, I'd like to introduce our recent efforts to understand the propagation of UV radiation in giant molecular clouds, which is essential to the understanding of reionization theory and possibly galaxy evolution. So we know little about reionization process in observations, and that's why numerical simulations are essentially the only tool to study this process. But this has been proven very difficult because simulating reionization involves not only the IgM scale, but also the small scale at which the Lyman continuum radiation is actually produced. As an attempt to cover both ranges, Yoki ran this spin simulation with a 10 parsec resolution and showed that dwarf galaxies alone may be able to ionize the universe by redshift 6 or 7 or so. I personally think that this is a great achievement, and many people in this workshop would agree with me because they probably know how difficult it is to produce reasonably looking simulations. However, we should move forward and ask ourselves if any of our implicit assumption makes sense at all. The most prominent issue is probably the finite resolution because it's true that we couldn't resolve the small scale of star-forming regions in this kind of simulations. So that was the motivation of this GMC simulation that we did a couple of years ago. So we tried a bunch of different star formation efficiency, basically to understand whether we are missing any important processes happening on small scales about the escape of Lyman continuum radiation. Because if you look at the galactic scale simulations, so this is a different simulation, by the way. This is not spins, but this is an isolated disk simulation that Teva Yu performed last year. And if you look at this individual region, you can see that this small star-forming region collapses and forms in star clusters, and the star clusters below the neighboring ISM. And as a result, the escape fraction increases rather monotonically. But if you have the turbulent structure inside your star-forming region and somehow allow the Lyman continuum photon just escape through these low-density channels, then the escape fractions will just fluctuate randomly. And if that is the case, then we might not be able to use this kind of simulation. But fortunately, when we tested with this simulation, the escape fraction sort of increases, monotonically, depending on what kind of star formation efficiency we put in the simulation. But to be fair, this simulation had limitations in the sense that, especially when it comes to star formation, because we put star particles by hand initially in the central 5 parsec region. So we had to run different simulation, improved version of the simulations with more self-consistent star formation recipe, like a single particle algorithm. So while I was working on this, after the meeting, the Ramses user meeting in Lyon, Sam Geen contacted us and asked whether we are interested in their GMC simulations because they have ran this simulation already with the single particle algorithm. But at that time, Sam was more up to small GMCs like the mass of 10 to the 4 to 10 to the 5. And I thought that this might be a bit small for the system that drive the reionization in high redshift, in the high redshift universe. And then this nicely looking guy called Jeremy suggested to run a bunch of new simulations, GMC simulation, and that was the motivation of this pre-line simulations. So this is a radiation magnetohydrodynamic simulation with using Ramses. and we used a pretty high resolution with various forms of feedback, including photoionization, supernova, and most importantly, we are now including sync particle algorithm in the simulation. And the idea here is that we want to check, how different types of initial conditions, change and affect the escape of Lyman continuum propagation. So we changed a bunch of different things, including surface densities, morphologies, turbulence strengths, and metallicities, and cloud masses. And so far, we have run 20 or so simulations in German and French, Korean, and Dutch HPC facilities. I forgot to play this movie, by the way. This is the composite image of the density and temperature and the flux. And you can see that once you form some stars, this disrupt the neighboring region pretty rapidly. So you can see the time scale here. And you will see that this entire cloud is dispersed within a 5 mega year or so. And then we begin to have these supernova explosions after we just completely disperse the central concentration. So compared to our previous work, we have increased the resolution by a factor of 3 or so, and we have changed, or we have included more initial conditions and also sync particle algorithm. Showing in the surface density versus the cloud mass. These gray symbols represent the observed GMCs from different galaxies, LMC or Milky Way or NGC 4419. And here our simulated galaxies are shown with the colored symbols. So this SM5 is a spherical cloud with a mass of 10 to the 5. So this is a small one, and this is a larger one, SM6, the 10 to the 6 solar mass. And you can see that there are 2 different points because we have a density profile inside the GMC. So if we measure the surface density inside this small region, then surface density will be sitting here, whereas this one is a really dense case. So we are simulating a very extreme condition for this particular case. And we have also the homogeneous cloud to facilitate the comparison with other studies. So this is more homogeneous compared to this one, you can see. And we also have the filamentary clouds. And here filamentary clouds share the same initial condition, but we have used the different velocity fields so that the structure becomes a more filamentary. So the general evolutionary trend of the GMCs are as follows. I mean, as you have already seen from the movie, it forms the stars locally, and then it just disrupts the entire cloud within a few megayear or up to 5 megayear. And the escape fraction increases monotonically, as I showed before, as the GMC is disrupted. And we have compared the escape fraction for different cloud masses and surface density, metallicities, and turbulence. And we found that the escape is more efficient if the GMC is less massive or less dense or metal poor, or the if the turbulence strength is weaker. So I'm happy to go over one by one, but since I have limited amount of time, I will just move to the next slide. So since I kept saying that this escape fraction is related to the disruption of the GMC, you may wonder whether we have a nice correlation between the escape fraction and the destruction timescale. So here I define the destruction timescale as the timescale at which 90% of the dense gas with 100 atom per cc is dispersed. And you can see that here these colored points are our simulation, and they don't show a very clear correlation between the two. And this is understandable because even though the cloud is dispersed to the density less than 100 atom per cc, there could be still neutral gas that is blocking the Lyman continuum radiation. But if we expand the sample and perhaps include the other simulation, like Kimm or Stryker et al., where they simulate a lower surface density than our cases, then you may be able to find some sequence like this. But this has to be, I mean, we have to run something similar in the near future to confirm this data. More interesting is probably the escape fraction versus the total star formation efficiency. So when I first ran the simulation, I thought that the escape fraction would increase with the increasing star formation efficiency. The idea is that if you form more stars, then you basically run out of the gas, and so the disruption might happen very quickly. But in reality, what happens is that if you have, in order for you to have this high star formation efficiency, you have to have high surface density. And the higher surface density means that the propagation speed of the ionization front is going to be delayed. And as a result, the escape fraction becomes smaller as you have a higher total star formation efficiency. In the other regime, where you have just little star formation, you basically have a limited number of Lyman continuum radiation, so it's not surprising to have the lower escape fraction with the decreasing star formation efficiency. And here, one of the interesting points is that even if you have a really bursty star formation, the result could be, the resulting escape fraction could be lower than this intermediate star formation efficiency cases. So there could be a sweet spot where we can extract the maximum or most of the Lyman continuum radiation. These escape fractions on GMC scales range from 20% to 70%, and this might sound a bit high for anybody working on reionization. Yes, thank you, Adrian. And I'm happy to answer to this, but basically, if you have ISM and ICGM, then you can just bring these numbers down to 5% quite easily. And since we are simulating the Lyman continuum radiation, if the observed part, if there is absorption of Lyman continuum, that will produce a Lyman alpha radiation, Lyman alpha photons. And the Lyman alpha photons are very useful to infer galaxy kinematics as well as the optical depths in the galaxy. So here I probably have shown this plot already to some of you. And if you have the optically thick medium, then the emergent Lyman alpha emission, that the separation of these two peaks will be larger. So this is the separation of the two peaks is often called this velocity separation, and this is essentially a measure of the optical depths. And if we compare the relative peak between the height of the double peak, if the medium is expanding, because the Lyman alpha is a resonant line, you tend to suppress the blue peak compared to the red one. And conversely, if your medium is contracting, then your blue peak is going to be more pronounced than the red peak. So by looking at the relative ratio between the two components of the Lyman alpha, you may be able to infer some kinematic information from the galaxy. So of course, if we want to know a little bit about the galaxy kinematics, we definitely have to start from the GMC scale simulation, and that's why I like this simulation. So we post-processed the GMC simulations with the Roscas and found that the clouds are bright in Lyman alpha when they are being efficiently destroyed. So Lyman alpha is not really bright when all the gas is dispersed. This is brightest when the gas, there is still quite a bit of mass there, so that it provides the Lyman alpha emission. And we have computed the Lyman alpha for a bunch of different conditions and measured the velocity separation and plot it as a function of the F900, which is the escape fraction at 900 angstrom. So this is similar to the escape fraction of the Lyman continuum radiation. And you can see that the observed galaxies are sitting here. And you see there is a negative correlation between the two. this is understandable because this is a measure of column density, and this is also a measure of column density. So if you have a higher column density, then it will move this word, and it will move that word. So you have this negative correlation. And if we plot our simulation results, they are all lined up here, meaning that if we want to reproduce that result, then we need some sort of a clumpy and turbulent ISM. Because if we have a uniform ISM, this will follow this sequence. And this is well established. And we can also we can also check the blue to red ratio, which is, like I said, is a measure of kinematics. And our simulated points are clustered here, whereas the measured, we actually observed the galaxies are somewhere sitting here. So there is a big gap between the simulated GMCs and the galactic observations, meaning that we might need outflows that are enveloping these GMCs. So this Lyman alpha could be essential, a very useful tool for the study, for studying the kinematics of the ISM and the CGM in the long run. So I will leave you with my conclusion here and take questions. Thank you.
Excellent. Thank you, Taysun. Eric, can you give us your question?
Yes, thanks a lot for this very nice talk and impressive work. I have just a question of detail. So your GMC is at a scale of a couple of 100 parsec, so as I understand from the initial conditions. Do you have any surrounding pressure that mimics some kind of gravitational potential around? I mean, you're in a regime where the self-gravity is dominating, I guess, but do you have anything around in terms of fixed conditions or not?
So we have a background medium, but unfortunately we didn't apply any gravitational force acting due to the galactic disk. But this the GMC we are simulating has a very high density, so they are essentially free falling. So even though there are some background pressure,
the disruption time will probably not change much anyway, as I think you emphasized this. But it's just to emphasize that the recent work really converged towards the thinking that these GMCs are in equilibrium until self-gravity dominates, but that the outside pressure is quite important actually. Maybe it's not. I think it's not going to change anything in your result.
Thank you.
Thank you. Okay, another question, Maxime.
Yes. Hello, Taysun. Thanks for the talk. I'm wondering, in the part where you were talking about Lyman continuum, you basically said that you can get very high escape fraction and you're missing some of the interstellar.
Maxime, can you maybe go closer to the laptop? I can barely hear you. Yeah, yes, it's better now.
The microphone was really low.
Yeah.
So yeah, and when you were talking about Lyman continuum, you were mentioning that you are missing the interstellar medium to make the escape fraction going from 70% to 5%, for instance. And at the same time, when looking at the Lyman alpha, it seems that your peak are way closer than they are in observations. So do you know how much gas would you need to get the escape fraction low enough? And if you get that amount of gas, do you get the peak separation higher because of the transfer in the ISM, for instance, or something like that?
So this is something that we are trying to get it right. Not only just the Lyman continuum escape fraction, but also the Lyman alpha properties. And what we learned so far is that if you just include the uniform medium with the different column density, that's not going to solve this problem. You will have to invoke very clumpy medium where some of the Lyman continuum radiation just escape through the holes, whereas Lyman alpha still scatters quite a bit. And this is possible because the absorption cross-section to Lyman alpha is usually higher than the Lyman continuum radiation.
Really nice. Thanks.
Okay, if there are no more questions, I think we need to move on to our last talk. So Sam, can you please put up your slide?
Yeah, give me a second. All right, okay, so I turned on subtitles. They are normally pretty good unless I say a proper noun or someone's name, so I apologize. All right, so I am currently based in the Netherlands, and I'm going to be talking about stellar winds and what they do and what they mean for Ramses simulations. And this is partly because I work with groups that look at stellar winds, and also I like to be contrarian and discuss new things. Yeah, okay, all right. So I think the last Ramses user meeting I went to was 2018 in Lyon, and I think my perspective at that time was stellar winds don't do very much. They cool very efficiently, and photoionization is the main feedback you need. And today I'm going to talk to you about how stellar winds are good and important, and photoionization is wrong, or kind of. So follow me up. And in general, I kind of like a sort of contrarian view of science, where you're always changing your opinion and discovering new things. I think that's kind of more exciting than discovering something and then leaving it discovered. All right, okay, so why do I bring this up? So a lot of simulations, from Jim Dale's simulations in 2014 and more recent ones, work that I've done, and also a recent paper by Lachlan Lancaster, which has a very nice analytic model, by the way. Say in general that winds shouldn't do very much, that they cool efficiently, and they create X-ray bubbles inside clouds, but in general, photoionization is a more powerful tool for driving out clouds, as Taysun showed in the last talk. But recently there have been some observations that suggest that actually winds are driving a lot of nebulae. So for example, this is M42 and Orion, which Cornelia Pabst in the Sophia collaboration at Leiden was looking at. And so their paper suggests that actually this is a wind-driven bubble, and that photoionization is not doing very much. So why is this? So the Orion Nebula is driven by a 35 solar mass star. It's full of X-ray emitting gas. A curious thing is that the region is not, while it's roughly spherical, the star is actually on one side and it's constrained by dense gas on the other side. It's about 4 parsecs wide and expanding at about 30 kilometers per second. Cornelia thinks that this is because it's driven by a wind bubble, although they use a fairly simple prescription where they're just comparing to the Weaver and Spitzer solutions. But I think the most interesting thing is that it's surrounded by neutral gas, or at least gas that's not completely photoionized. So this means that it's not a champagne flow. So you don't just have this unconstrained photoionization outflowing away. And there's also apparently no strong evidence of X-ray cooling. So how do we compare this to simulations and actually kind of close the gap between what observations and simulations show? So I'm going to be talking a lot about science in this, but I think it's really important in the Ramses meeting that we focus on how we improve the code and our understanding of how we use the code. So I'm going to gradually move in that direction over the talk. So like I said earlier this year, we published this paper where we did a first test of this. So we used a turbulent cloud similar to the one that Patrick's group uses, like Ifrig et al. In 2014. So we refine on the genes criterion, so basically dense structures refine. And because we want the star to form in the right place in the cloud, we use sink formation, and then when the sink accretes enough mass, then we form a star, and we can pick the star's mass. And basically all this mass does is it allows us to trace a stellar evolution model. So we use the Geneva model and some correction for the terminal velocity of the winds, because the wind is accelerated by radiation pressure, which is typically a factor of a few more than the surface escape velocity. And we emit both FUV and EUV for tracing radiation pressure and photoionization. And to do this, we made a general feedback module, which also Rebecca Beery was instrumental in creating. So I don't know if she's here, but I think she's currently on parental leave. Merging this is kind of something that we want to do, but obviously we kind of need to talk to people to figure out, what we overwrite and so on. So based on these simulations, without really kind of going into detail, it looks a bit like Orion, so it has a flow in one direction. The expansion rate and radius are roughly similar, although because it's so turbulent, the expansion rate varies hugely. But the cons are that, so the wind bubble cools very efficiently, and also the ionizing radiation has escaped into a champagne flow. So this is not a perfect Orion analogy. So how can we do better than this? Okay, so I did one thing which I like doing is analytic models. So I went back to the Weaver 1977 paper and re-derived it for a power law density field, because that's my idea of fun during lockdown. The reason I did this for a power law density field is that if you look at where stars form in simulations, you get a power law density profile. It's not completely uniform. Stars form because matter collects into a central density peak. And so here's a picture, for example, of the density distribution around one of our sinks. And because it's a sink particle, it's created some of the matter around the center. But you find this in even higher resolution simulations like the Lee and Hannibal simulations, for example. So if you rederive the Weaver solution, the stored energy, instead of 5/11 times the amount of energy emitted by the wind, it's corrected by a factor with the power law density field. But the most interesting thing is the radial expansion, which is corrected by a power law of 1/5 minus W. So basically what this means is that if you have an isothermal case where W is roughly -2, sorry, that should be 2 actually, that's shouldn't be minus, then the expansion velocity is constant, which is kind of fun. So it's if you think your wind is expanding into an isothermal density profile, then it's very easy to tell how fast it's expanding because it's completely linear in time. All right, so what does this mean for ionizing radiation? So in a situation like Orion, you have this dense gas, which is constraining some solid angle, which can be 4 pi, in which case there's no gas, with no dense gas constraining it. And then you have this expanding wind bubble. And then around that, the ionizing radiation travels through the wind bubble because it's already collisionally ionized, and then photoionizes some of the shell, and then some of the shell remains neutral. And then at some point, the shell becomes completely photoionized, and then it escapes into a champagne flow. And it turns out if you solve analytic models for this, so there are some hydrostatic approximations you can do to calculate the structure, you can actually trap ionizing radiation for a long time. So regions like Orion can easily have neutral shells and block these ionized champagne flows from happening. And thus you can reproduce the fact that there is some neutral gas around. So Ramses doesn't have a 1D spherical coordinate system, so I wrote my own. So I used a simple off-the-shelf hydro code called VH1, which I found online. And then I used a Python wrapper with F to Pi to produce this. And it also has various things like a real-time visualization option, which is nice. So I gave it to a couple of students and they were able to do simulations on their laptop without command line programming and do some fairly nice science fairly quickly. So if you're interested in this, email me. It requires some compilation. So it's not completely out of the box working, but it has a lot of examples and things. So here's an example run a bit like Orion where we pick a power law density field, roughly the right star, and we have some model for radiation pressure and simple dust. And it traps the radiation. So you can see the ionization fraction drops once you reach the shell, and so it doesn't escape. And at some point, once you reach a large enough radius, it escapes. Okay, so this picture works in 1D. So what about 3D with Ramses, which is what we're interested in? So what new physics do we need? So I took a few guesses as to what we weren't doing in the previous paper. So one thing was refinement. So, maybe if we're not refining on pressure gradients, we're not resolving the shell properly. And so, the photons are escaping too easily. So I turned that on. So we're using magnetic fields, but the runs with different magnetic fields and cosmic rays are in progress. So apologies, Johan, I will get to this very soon. But another big thing that I think was discussed a while ago is that in Eulerian codes, if you have a very hot shock with cooling, then they tend to overcool. And part of the reason for that is that the shock has to move across grid cells. So you have a picture here where you have a wind source and then some wind bubble moving across a cell. And so the hydro solver, the Riemann solver should do this fairly accurately. But the cooling module doesn't know that you have a hot bubble and a cold dense bubble. It thinks you just have warm kind of medium density gas. And so if you look at the cooling function, if you have a small density and a high temperature, that's fine, it cools inefficiently. If you have a high density and a low temperature, that also cools inefficiently. But if you mix them together, you get a super high cooling, and you find that this is where all of your cooling is in the wind bubble. So I'm not going to discuss the effect of turbulent mixing, which is some physical subgrid reason why you would experience high cooling. But what Vierlinger et al. And did was simply mask out the cooling in the context discontinuity. So Gentry's argument was that if you use a Lagrangian code, this goes away because your grid follows the shock. But I didn't do this, obviously. So what happens if you simply remove the cooling in this cell that's somewhat artificial? So here are some simulations where we have a 35 solar mass star in our fiducial Orion-like cloud, and we apply this cooling fix and see what happens. So if you just have UV radiation, then, so this is showing basically the warm gas, so the emission from photoionized gas, more or less. So you have this nice champagne flow here where the star is forming and then it's evaporating out in one direction. And if you just have wind, you have a small hot bubble. But if you add them two together, then suddenly you start trapping a lot of the radiation. So you have a little blowout here where you can see some pink gas, which is just coming out, but it's a lot smaller than just UV. So this is fun because feedback is no longer additive. So you're not just adding together different effects and producing more feedback. The effect of strong winds is actually stopping all of this photoionization. So a couple more tests. So in the top line, I tried a run with refinement and the cooling mask that I showed you in the last one. But if you turn off this cooling mask, then suddenly the feedback is super, super efficient. And the reason is that the density in the photoionized shell is balanced by the pressure from the wind. And if the wind pressure drops because it cools, then suddenly the density in the photoionized shell drops and suddenly it's super efficient to expand. And actually, if you don't include refinement, then this picture actually is a bit weaker. So somehow adding refinement and this wind bubble really increases the expansion. So this is something which suggests that your physical choices are very important. And also another thing I did, which I did before with the yield simulations with just photoionization is we looked at the effect of different random seeds. So for example, here is exactly the same simulation. We just changed the initial turbulent seed at the start that we used to generate our clouds. The density of the cloud is the same, the mass of the star is the same, but the picture is very different because the star forms in different places. So here you have a star that forms on the edge of the cloud. So even with this cooling mask, it escapes efficiently. And then you have a couple where the wind bubble is constrained, and then a really fun one here, which seems like it's producing Vishnyatic instabilities. And I don't know why only this one is doing that. So that's very cool.
3 minutes, Sam.
Yeah, perfect, thanks. So I am still figuring this stuff out. Okay, so where from here? So Taysun's already mentioned the Praline's suite of cloud feedback runs. And the reason this is important is maybe, this doesn't happen in all regimes. So like I said before, there's some papers looking at the effect of turbulence. And if you have very efficient turbulent mixing of your wind bubble, then it does cause it to cool down. And so photoionization maybe has more of an effect. But possibly another thing is that if you have a photoionized shell, maybe this actually disrupts turbulence by creating a buffer zone. So this is something that's still very exciting to look at, and I hope we discover more. And also I'd like to highlight these papers by Chongchong He and Massimo Ricotti and myself, looking at very high resolution versions of this, where Chongchong was actually looking at things like the stellar IMF and escape fractions and so on, and able to constrain the parameter space. So I think this is still a very exciting problem, and I'm still very excited to prove myself wrong year on year. Feedback is very complicated, and the difference between basically right and completely wrong is very small. So for winds, the big question is, do they cool efficiently? And if they don't, they can do a lot of weird, nonlinear, interesting things. Okay, so my take-home message is, let's do better than the simple analytic prescriptions that are decades old at this point. And that combining simulations and actually thinking about problems with analytic models to answer specific observationally motivated questions is the key. And that is the end of my talk. Thank you.
Thank you, Sam. So questions. So Patrick is the first. Please.
Thanks, Sam. Very, very nice work, and congratulations for not giving up on the wind, which are a nightmare, a nightmare, as we know. Yeah, so I think you mentioned the very important issue of the turbulent diffusion, but what about, I mean, I certainly agree that this has to be clarified, because following your talk, this could completely change the behavior of the cooling, but there is another process which is equally important that I was surprised you didn't mention, which is just thermal conductions. I mean, thermal conduction in the hot and warm gas is actually not small at all. I mean, the field lengths can be 0.1 parsec, 1 parsec, so that can create big regions, which is kind of transition that is not sharp between the two. That should be included. Huh?
Yeah, so I mean, this is the interesting thing. So I talked to some people doing supernova remnants here. So one of the questions is whether magnetic effects has an effect on conduction, which, yeah, I mean, also, you know, evaporation and things like that. So yeah, go ahead.
No. I mean, I agree that magnetic field may change the speed-jar conductions for the electrons, but it may also depend a bit of the neutral if you have neutrals there. I mean, it's a complicated problem.
Right. Yeah. I mean, I think definitely it should be included. So yeah, a combination of subgrid turbulence somehow and thermal conduction is very important.
Yeah, and if your field lines are wangled like that, then your thermal, yeah, I think it's a difficult problem.
But yeah, I mean, you definitely highlighted that the problem is that all of this stuff is subgrid even on a cloud scale.
Yeah, no, it's a difficult problem, but thank you for raising this issue. It's very interesting.
Cool.
Excellent. Any other questions for Sam?
And I do have my baguette for lunch since it's the Ramses meeting. So.
Perfect. Johan.
Johan.
Yes, sorry. Can you hear me?
Yes.
Okay. Can you go into a bit more details about how you hack the cooling module?
Yeah, so it's pretty similar to your cosmic ray shock finder. So basically what I do is, so at some point in the cooling module, I scan through every cell and find the neighboring cells in like this 3x3 grid, or 3x3x3 box. And then you basically look at the temperature either side of the cell. And if there is a discontinuity from very hot gas to not very hot gas, then I simply turn off cooling in that cell. So it's a very simple hack. And yeah, I think, you know, things like looking at the turbulent velocities across the cell would also be super useful.
And any idea what is the typical spatial resolution you need if you want to resolve the shell and get the cooling right from first principles?
This is sort of hard. I mean, so if I show you the picture here, for example, so I think the spatial resolution to resolve the photoionized shell is not super fine. I mean, you can do a back of the envelope calculation where you simply look at, you know, the pressure balance between the wind bubble and the photoionized gas, and then how much mass you basically need, and you know, calculate the shell thickness. So this is all, I think this is coming out in my analytic paper. But the big problem is in 3D, because then you have things like instabilities and clumping and so on. So what I think is happening in this very you know, bright image where you have a lot of photon ionization escape is that when you suddenly reach some lower density, then fragmentation or something really accelerates away, and you have this kind of runaway effect.
So just a comment, once you put conduction, if one day you put it, it will be you know, better for in terms of resolution because it will thicken the shell naturally, right?
Right. Yeah. Yeah. I mean, if someone wants to discuss conduction, I'd happily include it. I think this is a very sort of maximalist, I want the minimum cooling possible model, and yeah, I think well, maybe cosmic rays would reduce cooling, but yeah, thermal conduction and turbulence would probably increase the amount of cooling again. I mean, another thing to point out is Orion is very young and very compact, and so this is maybe also where the cooling has the lack of cooling has the most effect.
Okay, and one last question from Harley.
Hi, Sam. Really nice talk. I also have questions on the cooling. So if you're using some sort of shock finder to determine which cells you're shutting off cooling in, why not just try to refine those cells after you found them? And then instead of doing like the direct injection refinement, which I think is quite common in cosmological simulations, you use some type of slope across the cell and then only turn off cooling in like right exactly where the shock is, because I guess the worry is keeping the gas that should be cooling hot for too long in that method.
Yeah, I mean, that's possible. So what we're currently doing is refining on pressure gradients, but yeah, maybe that's actually a cheaper way of doing it because, you know, pressure gradients you can have in different regimes as well. So yeah, I don't know what the effect of doing that would be. It may be some non-linear thing like this. It may not be. But yeah, that's a good suggestion.
Okay, and on that note, I think we're ready for lunch. Let's thank all this morning's speakers with these clapping hands.
Yeah, thanks for sharing.